E11.
Oh, what's E11?
It's a it's just a little study group. Or technically it's a classroom, but nobody like uses it. It's always open, so we just go with my friends.
Oh, people do like SI and stuff, right?
I mean,
Sometimes.
yeah, sometimes,
Yeah.
but it's just a study room at that point. And here's the one of my friends, right? He's a civil major.
Yeah.
And couple of them are around the utility class. Like he said his was like extremely cold. Like he said it was cold enough to like run across your head. And I was like, you know what? I'll take his word for it. And initially, it wasn't actually cutting. Like it was like,
Yeah.
and then like I was like, you know what? Since it's not cutting, I'm gonna put pressure and I actually cut my hand. But I was like, damn.
I feel like you deserve that.
Yeah. Like honestly, if I was like, yeah, honestly, the first.
You like okay though? It didn't go too deep, just a little.
Yeah, it was like a paper. Or I would say it's a little bit worse than paper clip.
Like a cat gotcha.
Yeah.
Man,
Yeah, but
don't trust people's opinion of their blades.
I didn't press heat hit my trunk, and this was the only advantage I had. So it looks worse than it.
You can always go to the health center right there. They'll patch you up.
Sure.
I always forget that's there.
Yeah, I forget that there's
Safe space.
It is. Yes, that. Suspension. Difference. But it was like, it was too much machine. Someone tried to use it really sharp. He's got the ball and everything.
I mean, that's a back game up for you. That's what I'm saying.
Oh, no.
You guys have to, I do.
What's the
issue say?
With the pencils.
I
know
know Brandon does.
I think he has. Stone.
Tell me. That might.
Oh, yeah, he uses computer. Cause,
I use Ansys. No, I did, yeah, I did the first half here. And I saved it on my computer, but I forgot to zip file it. And so I did the second half with the fucking like bike frame.
Yeah.
And I did that at once. I was like. No, but I just did file.
Well, yeah, that's it. Oh, yeah, dude, I was so confused. In the morning? Yeah, it's like, looking there, I was like.
Was it like?
Are you in the same bathroom?
Yeah, have we got a mouse?
No, I need to get a mouse.
Yeah, it's more without you.
Yeah, the trackpad, it's like, it's so sensitive.
It's not even 80. Right, just.
You can't really do like,
No, you don't know back mouse is all. Awesome. You got a new desktop, his mouse. It's the shit.
oh, it's, you went to his house.
Yeah, it's not even like a laser, he has the ball. Like,
Oh, wow.
literal ball in there. So he's like, you're trying to fucking science and why.
I mean, I just got a basic with the basic.
No, I got the,
Talk to the
you
professor.
Like, it's $10.
Just talk to Sad.
And this looks good?
He asked us, he's like, if you want to switch, let me know.
those are for like the office.
We'll make it happen.
It's supposed to be ergonomic, so your hands like this the entire time, which is like kind of nice.
Does it ever like?
It's also like super nice.
Satellite?
I think that's kind of like the.
Forgot, is it a boat? I forgot what they're using, I don't know if they're using with my.
It's like it
Satellite.
I like my.
How about,
Yeah, so
That's like.
That's
What I'm afraid is if somebody uses.
Yeah, I don't think it'll take you long, it's just, I have to do.
Oh, I see.
something nowadays, everything. Yeah, it's put up my own instructions from Dr. Novus, yeah, finding the time.
You can do is like.
And he listens to another question.
So-
Oh, really? Oh, shoot.
You should.
Hey.
He was listening. Yeah.
I asked originally for, because you said you had the number.
What is it for just like?
They're like.
Okay.
Okay, they just need to be over.
Wait, what do you?
The Amazon basic.
Yeah, you have.
Huh?
Oh, we do.
He'll come back to you later.
Yes.
Do that,
Like,
I would
set that.
And they hired.
Yeah, what is your mouse?
I don't even. They don't pay as much as.
Why you doing it?
Is that on, they were my course, but. He's the same.
No.
Pretty same or something like.
Same,
Especially.
something I think is actually-
Yeah.
It's either that, or you're gonna start off like big slate.
You're gonna draw another.
You saw it, caught me so. I said that to Aiden.
I don't
All right, it's 5:30, let's go and get started. All right, good evening, everyone. How's everyone doing today? That's good to hear. That's great feeling that way in week 5. I know this is when things get stressful, so feeling good is. Okay, so today we're gonna start kind of today's kind of the beginning of kind of I would say kind of a 2.5 week long journey of diving deeper into meshing, right? So we've talked briefly about meshing at this point. You know, we've talked about what it is and kind of what the general ideas of kind of how meshing works. But today and well, Thursday we're doing an activity, but today, all of next week, and then the Tuesday after that, we're just going to be talking about element types, different elements, and how those all go. Okay. Okay. So some announcements, or one announcement, is that our next ANSYS activity is going to be this Thursday. Okay. So make sure you guys are here for that. ANSYS activity 3 is kind of the turning point. So ANSYS activities 1, 2, and 3, I consider those to be kind of the basics of ANSYS. And so, we're kind of still at that point right now. We're still kind of getting used to the software. We're getting used to kind of what it can do, where all the buttons are, how to configure the display and things like that. So activity 3 will be kind of the last of the basics of ANSYS. Starting with activity 4, and then activity 5 and 6, and then if we have time for more after that, those will be kind of more advanced features that you may not see in every single ANSYS project that you do, but they're still important. But activities 1, 2, and 3, I would say the stuff we're going to cover in these 3 activities you use in kind of almost every single project that you do in ANSYS. Okay. And so after ANSYS activity 3, I would consider you guys as kind of pretty familiar with the basics. And so next Tuesday, after we do activity 3, we're going to start talking about the midterm project. Okay. So the midterm project, basically, what you're going to do is I'm going to give you a part, I'm going to give you a CAD file, and then you're going to be responsible for doing a whole kind of finite element analysis on it. Okay? And of course, that not only includes the simulation, but that also includes the report that you have to write as well. Okay. So we'll talk a lot more detail about the project next Tuesday, but I just want to put it on your radar, and just know that the project, it will be due around Halloween. So it'll be assigned. I think next Tuesday is October 1st, and so you'll have about a month to do the midterm project. All right. Any questions I can answer before we get started for today? Yeah. Question.
What project, is it like a group? Or is it like per person?
It's individual, so it's all individual projects. Yeah. So there will be, so I'll give you a little preview. So I'm going to give you a choice of probably 3 or 4 different CAD files. And of course, with only 3 or 4 selections, there's going to be people are going to choose the same ones. But I expect everyone to do their own simulation and write their own. Okay. All right. Let's go ahead and get started. So for today, and next, and for the next 3 lectures after today, we're going to be talking about element types. Okay. So the types of elements that you choose and the settings for the elements that you choose, play a really big impact on your results, right? We've already kind of talked in depth about kind of the effect of element sizing, right? Element sizing is probably the single most important quality of your mesh that you need to specify. Okay. we've already discussed the effects of element sizing, right? So generally speaking, the smaller you make your elements, the more expensive your simulation is going to be, right? Smaller elements usually means that your mesh is going to contain a lot more elements. But the trade-off is that, smaller elements also means your results are more accurate, right? So that kind of understanding or that kind of, behavior is pretty consistent across all finite elements. So we're not going to be talking about sizing anymore. What I really want to discuss was, all the other decisions that you have to make with the elements. So choices on the element shape, choices on the element order, diving deeper into kind of what those actually mean and what those actually do, and kind of talk about what effect that has on your simulation itself. Okay, so for today, we're going to be going over 2D elements just because it's a little bit easier to start with 2D. And then next Tuesday, we'll be talking about 3D elements and how those affect the results. So, we talked about element shape and element order previously when we did our basics of meshing lecture. But, we kind of went over them quickly. We didn't go over kind of in detail kind of what that actually means and how that it affects the results, right? So let's go into that. Okay, so just to kind of jog your memory, for element shape, we kind of have two different options for element shape, right? And this goes for kind of 2D and 3D as well. So our choices for element shape is that, we can either pick a triangular element, which is going to produce a mesh where all the elements look like triangles. Okay. Or our other option is a rectangular shape. All the elements look like rectangles. The other decision we have to make is the order of the elements. So we can either pick a linear element, okay, or our other option is a quadratic. Okay, and so you can pick any combination of shape and order here. So you can have a linear triangle, a quadratic triangle, a linear rectangular element, or a quadratic rectangular element. Okay. So we're going to go through each combination and kind of draw out what the element looks like, and also talk about some of its properties. Okay, so let's start with the linear triangular element, the most basic kind of finite element that you can. In my grad course for finite elements, 541, I have my students start with the linear triangular element. That course is a little bit different than this one. In that course, I have them eventually write their own finite element code. And so when you're writing your own code, you're kind of building up the theory from scratch. Linear triangles are kind of it's always the first place to start. Okay. And so even though linear triangles, speaking honestly, they don't have they're not used practically in a lot of situations, especially when you're using kind of a sophisticated software like ANSYS. Linear triangles are always kind of a great place to start when you're first learning FEM. Okay, so what does it look like? So our linear triangular element like the following. So to start with, it's a triangle. Okay. And if you notice, I drew points at each of the vertices of the triangle. So a linear triangle has three, what I call nodes. Okay. We have 1, 2, and 3. Okay. And because it's a linear triangular element, what that means is that the shape function for the element is a linear function. I'll define shape function in a second, but let's write out what the shape function actually looks like for the linear triangle. And so for a linear function, and we're talking a linear function in two dimensions, okay? So that means we have both the x and y coordinates to deal with. Okay. We need to have all linear terms in x and y, and we need to have a constant term, right? So this is kind of the simplest linear function that you would have in two dimensions. Okay. So the symbol that I'm going to use for shape functions is a capital T, okay? And it's a function of our two spatial coordinates x and y. So our shape function in this case is C0 plus C1x plus C2y. Where all the C's, so C0, C1, C2, those are basically undetermined coefficients, but they are constants. Right, so those are simply just numbers that are in the equation. We'll talk about how to determine those numbers in a second. But again, you know, this function here represents the simplest possible linear function that you can have in two dimensions. Okay. So that's kind of what our linear triangle looks like. So our linear triangle has three nodes, and our shape function has three terms. Okay, so what is a shape function, right? So I kind of put up this this kind of mysterious function there. Let's define what a shape function is. And so a shape function is a property of the element, okay? And so basically you can think of it as a way for the FEA software, or the finite element method, to approximate the solution of the governing equation within that element. Because if you recall, you know, back when we first talked about meshing, right? One of the unique ways that finite element, or I would say kind of the way that finite element actually works, is that it kind of solves your governing equations in reverse, right? Normally, when you solve an equation, you know, you don't make any assumptions on what the solution looks like. So you're giving a differential equation, you just solve it. Just whatever the solution is, that's just what it is. Okay. But the way finite elements works is that, you know, the first thing that it does is that it assumes a form of the solution first, and then it solves for the best possible form of that solution that solves the equations. And that's kind of the power of FEA. And so, you know, when FEA solves for a solution, first thing that it does is that it assumes its form, right? And then when it solves for the solution, basically what it does is that instead of solving for a full function where, we have no idea what that function may look like. Instead, what FEA does is that it solves for the best possible values for these coefficients that mimic the solution as best as possible. And so what ANSYS is doing under the hood is that, it's assuming the form of the solution and then finding the best possible values for these coefficients, okay? And so just even from a high level perspective, you can kind of already see how this makes finding the solutions a lot easier using FEA, okay? Because if you were to solve a partial differential equation on its own, without any assumptions or anything like that, you're searching for, a function, well, trying to solve for a function is much more difficult than solving for just the value of a few parameters, okay? So that's kind of the basis of how FEA works. And so the shape function that's assigned to your element, it's kind of the central thing to, how the solution is actually going to behave, okay? And so as we introduce all the different element types, all the different combinations of element shape and element order, the thing that I'm going to kind of introduce right alongside it is the shape function for that particular element, okay? And so understanding the shape function and understanding its properties it's going to be something that's really important to know as you're kind of making your selections for the different themes. Okay. All right, any questions on this so far? Okay, good. Another thing that you'll notice, from this combination, you may have caught on already, is that the number of nodes in the elements matches the number of the coefficients in the shape functions. And so in this linear triangular element, we have 3 nodes, right? So we have 1 node at each of the vertices of the element itself, and that corresponds with the fact that our shape function also has 3 unknown entries. So the number of nodes in that element, must match. And there's a very good reason for this too, because the way finite elements is kind of a misleading name in some way, where a lot of people focus on just the elements themselves. But in reality, if you kind of open up the ANSYS code and you kind of see how it works, actually what happens is that the solutions are actually solved for at the nodes first. Right, and so if I kind of redraw the triangle here. And so just to make things a bit easier, well, let me label these nodes. So these are 1, 2, and 3. Okay. So just to make things a bit easier here, let's assume that we're solving a heat transfer equation. Okay. And so when I say that the solutions are solved at the nodes first, okay, what I mean by that is that if we're solving for, let's say, the temperature field, we're gonna compute the temperature at node 1, the temperature at node 2, and the temperature at node 3. Okay, so we have T1, T2, and T3. In order for our finite element solution to be continuous, right? And so in order for the solution to have continuity as you move from one element to the next, okay? The solution of the equations within the element has to match all the nodal solutions. That's a really important part because, even though you're going to be solving the solutions on each element individually, right? When you go from one element to the next, there should be some continuity in the solution, right? You shouldn't get something completely different. You shouldn't have the solution kind of have sharp edges, right? Ideally, okay? And so this actually kind of helps sets up a system of equations that we can use to solve for the unknown coefficients. So what this basically means that is if you evaluate the solution through the shape function at each of the nodes in the element, you should obtain the nodal solutions. Okay? And so for instance, if we evaluate the solution at node 1, so let's say that we evaluate the shape function at x1, y1, okay? So x1, y1 being the physical position of node 1. And so we plug that into our shape function. We have C0 plus C1 x1 plus C2 y1. You should get T1, which is the nodal solution. Okay, and so you can write a similar equation for the solution at node 2 or the solution at node 3. Okay. And so what that's going to give you is a system of 3 equations and 3 unknowns that you can solve for C0, C1, and C2. And so effectively, what you've created here is a system of linear algebraic equations for the coefficients. Okay. And that's really key because if there's one thing that computers are really good at, well, computers are really good at a lot of things, but one thing that computers are particularly good at is solving algebraic problems. Okay. And so the way that a lot of kind of algorithms work, and this applies to AI and machine learning too, is that if you can take a very complex problem and formulate it in a way such that it becomes an algebra problem. Now it doesn't matter so much how big the algebra problem is, and so you may have a system of 1 billion equations and 1 billion unknowns, right? As long as it's an algebra problem, the computer will be able to solve it. Okay. And so that kind of technology or that kind of way of thinking is actually powering a lot of really modern algorithms today. Finite elements just happen to be one of the first ones to actually do. Okay, so that's the basics of kind of the linear triangle, right? And so from here we're going to go on to the quadratic triangle and the quadrilateral elements and talk about kind of how those work. Okay. Any questions on this so far? Okay, cool. All right, so let's talk about the next step up. So let's talk about the quadratic triangle. All right, so once again, let me go ahead and draw the triangular element. So we're still in a triangular shape here. The only difference is that our element order here is going to be quadratic instead. All right, so we have our triangle here. One, 2, and 3. Right, so the shape of the element itself isn't changing. what's going to be changing is the order of the shape function. Okay, so let's see what a quadratic shape function will. Okay. So we're gonna be looking for the simplest possible quadratic function that's going to exist in 2D. Okay, so once again, we're in 2D, so we have to consider both x and y. All right, so once again, we have our shape function here, t of x and y. So even though I'm saying this is a quadratic function, we also have to include all the other terms that we've already kind of defined up until that point. Okay, so that means we have to include the constant term. So that means we have to include a C0. And then we have to include our linear terms as well. So that's these are all terms from the linear triangle, right? So we have C0 plus C1x plus C2 1. Okay, now we start to introduce the quadratic terms. And so the quadratic terms, you're going to have at least one variable multiplied by another. Okay? And so first one we're going to have is x times x, and so that's going to be C3x squared. If you have to have, and if we have x squared, we have to have y squared as well. So C1x squared, C3x squared, C4y squared. Okay. Another possibility that we can have in order to get a quadratic order term is to multiply x times y. And so that's going to give us our cross term, C5xy. Okay, so we have six terms here, right? So C0, C1, C2, C3, C4, C5. Okay. So there's a little bit of a discrepancy here, right? So remember, like I mentioned just a few minutes ago, the number of terms in your shape function has to correspond with the number of nodes in your element itself, right? So we have 6 terms here. We have 6 terms in our shape function, but our triangle here only has 3 nodes. And so, how can we make this triangle have more nodes without changing the fact that it's a triangle, right? And so, if you try to add 6 more points or 3 more points here, right? You would think that it would change the shape of the shape itself. So this is an issue that's kind of present in all quadratic elements, where there's just not enough nodes in kind of the base shape in order to support the shape function itself. But we want to have a quadratic element because quadratic elements have a lot of really nice properties that we can take advantage of in our simulation. Okay, and so the compromise that's actually taken here is to add what's called mid nodes. And so mid nodes are simply just nodes that exist in the middles of the edges of the element. Okay. So that means we're gonna have a node here, right? So we're gonna have a node in between nodes 1 and 2. We're gonna have a node here, right? That's in between nodes 2 and 3. Okay. And of course, we're gonna have a node there as well between nodes 1 and 3. So that's gonna be node 4, node 5, and node 6. Nodes 4, 5, and 6 are known as mid nodes. Okay, so they're nodes in that they're true nodes, and so we are going to be solving for the solutions at these nodes, but they're not the same as the vertex nodes, right? And so they're placed in the middles of the edges of the elements, but they don't change the actual shape. They don't change the direction of the edge, or they don't create a new edge, and so they're mostly just there just to have some additional points where you can compute the solution. Okay. Okay. So that's our quadratic triangle, right? So all the same kind of discussions that we had before about, the purpose of the shape functions and the purpose of the different terms, all those are the same here. The only difference is that, our shape function here is more sophisticated. Okay. So before we move on to the quadrilateral elements, let's compare these two elements and talk about kind of this problem. Okay. So one way that you can kind of quantify, how expensive or how costly each element is to count the number of terms in the shape functions, right? Or conversely, you can just count the number of nodes in the elements. So the more terms that there are in the shape function, the more expensive or the more computational cost, that element is going to occur. Okay. And so just looking at the different elements here, you can see that the quadratic triangle has twice as many terms as the linear triangle. So the quadratic triangle is going to be more expensive to compute on a per element basis. But we knew that already, right? So we kind of discussed before that quadratic elements on average are more expensive than linear elements, just because there's more terms to compute. Okay, but now you can kind of see the reason why the quadratic elements are more expensive. It's just there's just more terms to compute. Okay. But of course, the trade-off for this is that even though quadratic elements are more expensive, they are more accurate. Okay. But from the shape functions here, we can kind of qualify that statement a bit more in terms of what I mean by that. Okay. So because quadratic elements because quadratic elements have more terms in their shape function, they're able to capture more complex behavior of the solution within that element. And so, being able to capture more complex solution behavior, generally that equates to more accuracy, but sometimes it doesn't as well. Okay, it all depends on how the underlying governing equation is behaving within the element itself. Okay, so let me kind of give you a visual demonstration of kind of what this means. Okay, so a linear element basically says that we're going to find the best linear function that fits the solution within this element itself. Okay. And so for every finite element problem, every finite element problem, you're going to be solving an underlying partial differential equation. Okay. We don't know exactly what the solution looks like, but FEA is going to approximate the solution as best as possible. Okay. And so whenever you are doing computational work, and so this is true for finite differences, for CFD, finite volumes, whatever, right? There's always this notion of a true solution, right? So you have some kind of very complicated math problem that you want to solve, and that complicated math problem has a true solution, right? Or another way to say it, it has an exact solution. Okay. Okay. Let me go ahead and draw like this. And so let's say that we have an exact solution that kind of looks like the following. So this right here represents the exact or true solution. It's not quite a linear function, it's not quite a quadratic function, but it's the true solution. Okay. And so FEA, what it's going to do is that it's going to say that, all right, we don't know exactly what the true solution looks like, but we're going to try to approximate it as best as possible using the methods of FEA. Okay. And so a linear approximation for this, may look something like this. So this right here would be the best linear approximation. And so you can see the linear approximation, it's doing the best that it can, right? But it's limited by the fact that it's a line, right? And so there's only so many ways that you can arrange the line, right, to make it as close to the solution as possible. There's just inherent limitations to using a linear function to approximate a complex equation. Okay. Now it's probably cheap, right? So you probably didn't have to exert that much effort to find this linear approximation. But your solution is always going to have limitations because, if your true solution is not linear at all, then there's only so much you can do with the linear shape function. And so, when I talk about linear versus quadratic, this is kind of what I mean, right? And so there's, we're approximating as a linear function, but there's only so much we can do. Okay. In contrast, if you were to use a quadratic function, okay, right? One of the characteristics of a quadratic function is that you can actually have some curvature to the function itself. Okay. And that's really big, actually. So that's actually really important. And so, linear functions, although simple, they are not able to bend at all, right? So they're just their destiny is just to be a straight line. Okay. But quadratic functions, you can actually curve it to a certain degree. You can't curve it that much, but there is some curvature. And so an ideal, let's say the best approximation using quadratics, might look something like this. So in purple right there, that would be, what we consider your best quadratic approximation. Okay. So it's able to capture some curvature. It's not that much curvature because quadratic is only just one step up from linear, but the fact that it is able to capture some curvature is actually pretty important. Okay, and a lot of times that little bit of curvature is enough to kind of get you closer to the exact solution. So this is how things work in general, right? And so in general, you may have an exact solution. It doesn't quite follow a linear path, it doesn't quite follow a quadratic path. But generally, a quadratic function will do a better job of approximating that exact solution than a linear function. Okay. But if you have a situation where let's say that the solution to your underlying governing equation is a linear function or looks very linear, then in those cases, there's really no difference between the performance of a linear approximation and a quadratic approximation. So it may not always be the case that using quadratic elements leads to a better quality solution. If your underlying true solution is linear anyway, then you might as well just use linear elements because you're not really going to get any benefit from quadratic. Okay. Now, of course, that begs the question, how do you know if your underlying equation, how do you know if the underlying solution is linear? Well, that's kind of a deeper question for if you were to take 438 or 538 or something like that. So as you kind of solve a lot of these differential equations, you start to kind of build some intuition of what solutions are going to be linear or not. Probably by the end of class, the more you use ANSYS, you'll probably start to build that intuition as well. But this is kind of a trick that some people use to kind of save themselves on a little bit of cost between linear and quadratic. Okay, because if you can kind of reasonably predict that your solution is going to be linear, then you can make your elements linear and kind of save yourself a little bit of cost. Okay. That's just kind of one kind of small trick that kind of experts in finite elements that they try to use, try to limit the amount of cost that their simulations will take up. Okay. Because once you kind of get to kind of the expert realm or of people kind of using finite elements professionally, you're going to be using a lot of these kind of little tricks to try to make your simulations kind of as cheap as possible without sacrificing any accuracy. Okay, that's kind of the game that you're kind of playing kind of at kind of the profession. All right, any questions on this? Okay, cool. All right, so let's go ahead and move on. So let's go ahead and start talking about the quadrilateral elements. So just like the triangle, we're going to start with the linear version first. So we'll talk about the linear quadrilateral. So our linear quadrilateral element will have four sides because it's a quadrilateral, and also 4 nodes. One, two, three, 4. Okay. And now we have to write the shape function. So we have a linear shape function. Okay. But we have a little bit of a complication here, right? So let me write out our shape function first. Okay. So our shape function is going to be t of x and y. Because remember, we're still in 2D, and so our space variables in this case are still x and y. So let me go ahead and include, first we have our constant term, so we have C0. Then we have the term that's just linear in x, which is C1x. We have the term that's linear in y, C2y. Okay. So all of that is the same as the linear triangle that we had before. Okay. But we're kind of at a little bit of a crossroads here, right? So our element itself has 4 nodes, but our shape function here has only 3 entries, right? So 3 coefficients. And so there should be one more term, one more coefficient in our shape function here that is linearly independent from the other ones, okay? So it's not enough just to say that, you know, let's add another C3x, right? We can't do that because we already have a term that is just x by itself, right? So we can't have another term that's exactly the same as another one. So our 4th term here has to be different than the other ones. But we've already exhausted all of the linear terms, because if we add another, you know, we can't add x squared, because if we add x squared, this is going to make it a quadratic. Okay. And so, you know, kind of the cheat that we use for the quadrilateral elements, and we're going to use these for the hexahedrals as well, is that, you know, we can add the cross terms, because even though the cross terms are technically quadratic terms, so this, you know, one term multiplied by another, you know, technically it's only linear in each of the terms individually. So our last term here is actually going to be C3xy. Okay. And so we make our 4th term here C3xy, then it is actually going to be linearly independent from the others. And so we have 4 distinct terms in our shape function, even though the last one there is we call it pseudo-linear. It's not true linear, it's pseudo-linear. So it's not a true linear term because you have 2 variables kind of multiplied by each other, but it's individually in x and individually in y, they're linear. And so it's a pseudo-linear. Okay. Okay. And so of course, you know, if you compare this to our linear triangle, you know, that existence of that last term actually is what makes the quadrilateral unique. Because remember, we talked about kind of the purpose of the shape function is to approximate the solution behavior inside the element itself. Okay. One way that you can think of the shape function is that each term of the shape function represents a different mathematical capability. And so if you think back to the linear triangle only had capabilities to approximate a constant term, a term that's purely linear in x, and a term that's purely linear in y. Okay. This quadrilateral here has an ability to approximate a cross term. And so if our solution has any behavior, has any kind of characteristics that visually look like the function x times y, then our linear quadrilateral will actually be able to pick that up, okay? Whereas our linear triangle would not be able to pick that up at all, okay? And that's actually pretty significant because that cross term means that any kind of solution behavior where the x coordinate has to interact with the y coordinate the quadrilateral will be able to pick that up, okay? And when you're talking about structural simulations, there are a lot of solution behaviors that have kind of cross interaction between the different space variables. In fact, it's very common for the solution to the linear elasticity equation to have some kind of cross behavior. Okay. And so even though it's the addition of just one more term, that one more term actually makes a big difference in terms of how the solution actually behaves. Right? Remember, we talked about, in general, quadrilateral or rectangular elements will have better solution properties or better accuracy compared to triangular elements. It's precisely because of the existence of this term. So linear triangles, and this goes for 3D as well, and we'll talk about that next week. Right? Linear triangular elements don't have any ability to capture any cross terms. And that's pretty significant in some cases. Okay. All right. Another really important property of this cross term, we're going to be talking about the cross term a lot because it is actually really important, is that you actually are able to get non-constant derivatives from it. So what do I mean by that? So let's take our shape function, let's take the derivative of with respect to x and y. So just the first order derivative, okay? And since this is a multivariable function here, we have to take partial derivatives, one with respect to x and one with respect to y. Okay, so let's take partial t partial x. Okay. I'm going to take the partial derivative of our shape function with respect to x. And so if we do that, if we come back up to our linear shape function up here, we know that the constant term, once we take the derivative of that, it's just going to go away. And so C0 is not going to show up in our derivative. Our next term is C1x, and so we take the derivative of that with respect to x. We just end up with C1. Okay. So I'm going to go down and write that. Okay. The next term that we have is C2y, and so C2y is a non-constant term. But it doesn't depend on x at all. And so when we take the derivative of C2y, we end up with just 0. Finally, we have our last term there. We have C3xy. And so when we take the derivative of this with respect to x, we just end up with C3y. Okay. So let's take the other partial derivative. So let's take the partial derivative with respect to y. So partial t partial y. I'm just going to do this one really quickly just because it's pretty much the same as the other one. Okay. The only difference is that when we take the y derivative, our constant term is now going to be C2. And our last term there is going to be C3x. Okay. So once again, we see the cross term here coming up, really, really clutch for us because you can see, right? When we take the derivatives, the only thing that's preventing these derivatives from being constant is the existence of this cross term right here. Okay. And so this is actually really big because with the cross term, our derivative quantities can actually vary in space. Okay. And so you may be asking, why is that important? Why is it important for our derivatives to vary in space? Okay. So, once again, I'm going to try to frame this within the context of structural equations. Okay? So in structural equations, we're solving the equation for linear elasticity, where stress is equal to Young's modulus times strain. Okay. How do you compute strain? Right? Strain is nothing more than just the derivative of the displacement field. And so in order to compute strain in your structural simulation, you have to take the derivative of your solution, okay? And then from the strain, you're going to compute stress, okay? And internal stress is the driving force that causes, all the deformation that you see. So this is really important because if you have a linear triangle, right? The linear triangle does not have that cross term at all. And so what does that mean for the linear triangle? The linear triangle is thus therefore going to have constant stress throughout its entire element. There's just no mathematical way for there not to be constant stress in linear triangles. Okay. All right, and so that actually kind of leads to kind of a couple important phenomena. Okay. And so if you have constant stress, and if let's say that you have a fairly coarse mesh, right? That means when you jump from one element to the next, your stress may jump in value pretty dramatically. Okay. So that's one thing. And so one thing, it produces a solution that does not look visually very appealing. Okay? But it has, besides aesthetics, it actually has a very adverse effect on your simulation as well. Okay. And so if you have linear triangles, what can happen because of this constant stress phenomenon is you can get something called shear lock. And so shear locking is a phenomenon that kind of uniquely only happens for linear triangles. It's possible to happen for linear quadrilaterals as well, but because the quadrilaterals have that cross term, it actually helps guard against shear locking quite a bit, actually, surprisingly. And so what happens in shear locking is that the deformation in your model is severely underestimated. And so the reason for that underestimation is that, part of the structural equation, it relies on the fact that there is a gradient of stress throughout your entire structure. Right? And so it kind of relies on the fact that stress is going to vary from point A to point B. Right? But if you have elements in your model which, the stress state is purely constant, you know, that's not able to happen. And so, you know, you're gonna get, you know, possibly large sections of your model where the stress is just gonna be constant, just because, you know, the linear triangles aren't able to support any variation in stress, okay? And so what happens then is that if your stress is constant over a large kind of section or large area of space, then your deformation is not able to be solved for accurately. Okay, and so what ends up happening is kind of what you kind of visually see is that your model kind of locks up on itself. Where, you know, you could apply, you know, you could have your structure, you could apply a ton of force to it, but you know, it just refuses to move. It just refuses to deform. Right. So that phenomenon is known as shear modeling. And it's something that you want to avoid whenever you're running any structural simulations. All right, so the good news is that within ANSYS, it's actually very easy to avoid. And so the easiest way to avoid it is just to simply use a quadratic element, right? Remember we talked about with meshing is that, you know, for the most part, you know, there's no, at least from where you guys are at right now, you know, there's no practical reason to use linear elements, okay? And this is kind of more evidence to that kind of point here, where you know you don't want your model to lock up. You don't want these constant stress elements, and so you know the easy thing is just to use quadratic elements. But even if you do use linear elements, you know, linear quadrilateral will help kind of deter that behavior to a certain degree. Okay. But you know, ANSYS makes it really easy for you to just to switch to quadratic. And you know, for the types of simulations that you're running, you know, you're not really going to notice a big difference in the cost. And so, you know, you just want to avoid thinking about shear locking at home. And so, you know, the best way to do that is just to avoid, you know, avoid using linear elements whenever possible. All right. Any questions on this, on shear locking? Okay, cool. All right, so the last thing I want to talk about today is the last element type that we haven't talked about yet, which is the quadratic quadrilateral. Okay, so let's draw it first. So we have a quadrilateral shaped element, so we have a rectangular looking guy here. Okay. Let me start with all the vertices, and so all the corner nodes. Okay. 1, 2, 3, 4. Okay. But we know that this is a quadratic element, right? So we're going to add mid nodes as well. So in the middles of each of the edges, we're going to add some additional nodes. So that's going to add 4 more nodes to our element. Okay, so in total here we have 8 nodes. So this is the most amount of nodes that we have in our that we've seen in an element so far. Okay, so let's write out the shape function. And so our shape function here is going to have it's going to be quadratic, and we know that it's going to have 8 separate terms. Okay. Okay, so our shape function is going to be t, x, and y. So just like we've done previously, let's start from the constant term and kind of work our way up to the quadratic terms. So we have C0 plus C1x plus C2y. Okay. So those are all our pure linear terms. One property that your elements must have in finite elements, you know, we're not really going to go over it because we're not doing too much theory, is that your elements have to have this property called completeness. And so what that basically means is that, you know, if you're using a polynomial of a certain order, you have to include all of the lower order terms first before you get up to the higher ones. So that's why you see for all of the shape functions that we're talking about today, all the shape functions we're going to talk about next week, you know, they include the constant term and the linear term just because they have to be. Otherwise, your element wouldn't be complete. And just from the sake of solution accuracy too, it's important to have them as well. So if your solution behaves like a linear function, you want to make sure that your element captures that as well. Okay, let's move on up. So let's move on up to the quadratic terms. And so we have a C3 xy. Okay. So that's our cross term that was present in our linear quadrilateral. So that's going to be present here as well. Let's include the pure quadratic terms as well. So that's going to be C4 x squared plus C5 y squared. Okay. So that's 6 terms. And so those are the 6 terms that were in the quadratic triangle. And we have 2 more terms to go. Okay. And so our remaining 2 terms here are going to be our pseudo quadratic terms. So, you know, in the true sense, they aren't really quadratic because they're going to be 3 variables multiplied by each other. But individually in x and individually in y, they're going to be quadratic terms. And so we have a C6 x squared y plus C7 xy squared. Okay, so we have our most complex shape function so far. And so with all this complexity, of course, there's going to be cost, right? And so on a per element basis, the quadratic quadrilateral is going to be the most expensive just because there's 8 terms to compute. But it's also generally the most accurate, or it's the most complete in the sense that, you know, it can capture a very wide range of solution behaviors based on its shape function. And you know, I won't get into the details of it just like the linear quadrilateral, but the fact that we have these pseudo quadratic terms, the fact that we have these 2 guys at the end, you know, those actually make a really big difference in the solution. So, you know, when you take derivatives of that term, you know, you're still going to maintain, you know, dependence on x and y, right? And so you can have very complex deformation fields, and then by token very complex stress fields, very complex strain fields. And a lot of even higher order quantities as well. You can do this as well. Okay. So it's the most full questions.
That's why running sims on this opts for this more than triangle.
Exactly right. So if you can swing it, if you can mesh your geometry with quadrilateral elements, then that's usually the best option because it's going to give you the most complex behavior. Now, the downside of this is that it's not always possible to mesh with these quadrilateral elements, just because the meshing algorithms that exist out there, they're much better designed for triangles. And so the difficulty you may have is that if you're trying to use a rectangular mesh, you try to use a hexahedral mesh, you know, ANSYS may just say that the meshing is going to fail. And so in those cases, you know, if you have some complex geometry, you may end up being forced to use triangles. But if your geometry is simple enough, or you're able to kind of play around with the size enough so that you can swing quadrilateral rectangular elements, then that's always the best thing.
You're gonna have to be like very cubical shaped.
Yeah. Well, you'd be surprised. You know, the measure is actually pretty robust, and so hexahedrons and rectangular elements will work in cases where you don't think it would work. But then, for cases, usually when ANSYS says that it fails to mesh a geometry, it's usually because it's having a hard time putting. That's usually the case. All right, any other questions on this? Okay, all right, so that's all I had planned for today, and so when we come back on Thursday, we have another ANSYS activity plan, so that's ANSYS activity. So we got looking forward to that. So thank you guys for coming today. I hope you guys have a great rest of your day, and I will see you guys on Thursday.
It's like something that's
All of these books, guys, do like a check.
I mean, the doctors also.
No, the doctors.
We're gonna talk to my review. Check your mind.
Yeah, I've always seen like all the palms drawn and just like, yeah, all I am.
Dude, and then you got like a custom LED strip from the mustache. So black.
Doesn't need to. Wait, did you change the? Yeah. It's in the activity. Like, it's like you're not even. What? You don't believe it. This is the very beginning, right? I don't know. I mean, I triple down.
Yeah, but still free. Also, you're feeling.
The bike. So you do the bike.
This one better not get.
When your neck was hurt.
My last.